Hi, welcome to the Dr. Greenthumb IoT platform. Our IoT platform consists of an architecture whose goal is to achieve the best possible growth of the plants. The buyer receives at home a complete structure composed of several sensors and actuators that check out the plant's life status. Once the structure is mounted, it's just to start with a unique script that launches the complete software. First of all, the embedded device, sensors and actuators are automatically registered within the catalog. Since everything is registered, the background monitoring starts. It consists in an independently constant exchange of data in order to maintain plants in optimal conditions without any effort by the user. Moreover, as far as the user awareness is concerned, it is developed to have either constant supervision on everything that is happening and the possibility to directly activate commands. The Telegram bot can both activate commands of the actuators and see live streaming data, while ThinkSpeed and Node-RED provide a simple user-friendly interface in which data could be seen through historical graph. The hardware is composed of 3 relays, 2 DHT11 sensors, 1 light sensor, 1 soil moisture, 1 breadboard, 1 Arduino Leonardo, 1 Raspberry Pi. The complete hardware scheme is the following. In this slide is represented the use case diagram of our IoT platform. As it is evident, this platform exploits 2 different standard network communication paradigms. The MQTT protocol as publisher and subscriber, the RESTful web services both as provider and consumer. Information exchanged through these paradigms are in JSON or SNML format to avoid the possibility of misunderstanding among different actors of the platform, adding reliability to the system. There is also the communication between Arduino and the Raspberry Pi, where the UART serial communication is used in order to retrieve analog readings from sensors. The different microservices have the possibility to be started separately, but with a unique bash script that contains the information to reach the service catalog, to retrieve data from it and automatically configure itself. In addition, the whole system is built focusing on robustness, so that in case one of the actors is for any reason no more online, the other microservices don't crash. All the microservices outlined in the slide are built to work independently and to communicate with each other only through the internet.
The Greenhouse catalog is a central node fundamental for the coordination of the whole constellation of microservices in the system. It is the gateway access point for device connectors, control strategies, and user awareness microservices, so its address on the local area network, hence IP address and port, are known a priori by every other agent. It offers a REST interface on the network for request-response communications in order to make available configuration parameters to various microservices, keep track of alive registered devices by checking their obsolescence based on time, and making available their endpoints to whoever needs to address them. Catalog's REST interface offers GET, POST, and PUT methods. GET methods return requested information in JSON format. GET requests include MQTT broker info, where MQTT broker IP address and port are returned, specific box configuration, where box ID is passed as a query and catalog returns the box configuration with plant name, specific device configuration, where device ID is passed as a query and catalog returns device configuration parameters such as port, GPIO pin to which sensor or actuator is connected, and MQTT streaming period. List of all currently registered and alive devices in the system. List of all boxes which configuration is specified in configuration file. Specific registered device information, where device ID is passed as a query, and if alive or registered, catalog returns information about both its MQTT and REST endpoints. Truffle API parameters. It returns API URI and token needed for accessing its database. ThinkSpeak parameters. It returns channels, numbers, and various keys for accessing the service. Telegram bot parameters. It returns the token needed to access the service. Post method lets register a new device for the first time it enters the system, passing as a query its own IP address, port, REST, and MQTT endpoints. Put method is used only for periodic continuous requests by registered devices in order to be kept alive in the system and be available to other services. It requires the unique device ID to be passed as a query.
The level of the device connectors is divided into two main subsystems, the one dealing with sensors and actuators, and the other dealing with the web implementation. In the first one, we have the embedded sensors are both analog, to measure oxygen, brightness and soil moisture, and digital DHT11 to read temperature and humidity of the plant and of the environment. Analog sensors are assembled by the Arduino board, which can exchange data with the Raspberry Pi through a wired serial communication. Then each box contains three actuators, a fan, a water pump and a lamp. The second subsystem is the web implementation. In fact, device connectors let sensors and actuators be connected and reachable in the network. To communicate, they use both RESTful services and MQTT protocol. Working principle of device connectors microservices is similar for both sensors and actuators. On startup, both through a bash file, obtain the information to connect to the catalog, which are catalog IP and catalog port. They send a GET request to the catalog to extract all the needed information from the configuration file in SNML format. Each time a GET request is sent to the URI of device connectors, the script returns a JSON SNML file with all the characteristics of the sensors and another JSON SNML file with the current status of the actuators, on or off. Once they obtain all the information, they send a POST request to allow the registration of the device to the catalog. Later, every 60 seconds, PUT request will be sent in order to notify the catalog that the sensors and the actuators are alive. Then, each time a PUT request is sent through the URI of the actuators, it means that the status is changed from on to off or vice versa, and so the script will return an updated JSON SNML file with information on the new current status. Instead, as far as the MQTT interface is concerned, the script uses this protocol to allow sensors, once they are connected to the local broker, to publish the SNML file in a specific time instant, define string period in the configuration file over a specific topic, while the actuators are subscribed to their respective topics in order to receive SNML messages as control commands when these are streamed by control strategies microservices or manual commands such as those coming from Node-RED dashboard. If the catalog was to crash or it wasn't connected on startup, an exception is raised and attempts to restore the connection with the catalog are carried out periodically every 60 seconds.
The aim of control strategies is to produce control commands for actuators autonomously through an algorithm based on plant characteristics and on real-time data retrieved from the sensors. each actuator receives command from its own control strategy, so in our case there are 3 different scripts, for the lamp, the water pump and the fan. These scripts need an additional a priori information, the box number, to have the possibilities to control multiple boxes simultaneously, each one with its specific controls, just launching same script twice or more with a different box number. First, the scripts collect all the information from the catalog needed to be able to work in an infinite while cycle. The aim is to communicate with sensors and actuators through the MQTT protocol. In addition, the Trefoil.io API is used in order to reach the best possible growth for plants. As a matter of fact, this API stores specific characteristics for each plant. If and only if all the needed information are obtained successfully, the MQTT protocol could start to communicate with the sensors. A check method is implemented to be sure that all the requests done have a status code of 200. Before the core control part starts, 2 methods are implemented. One is used to check that the payload of the message received is not empty. The other one is used to check that at maximum 5 minutes pass from 2 consecutive messages received from the sensors. In case one or both check methods fail, the control could not start and the default message is printed as output on the terminal to be used for debug purpose. As an additional feature, the script reboots itself every hour, checking that everything is still online and no problems occurred on other softwares. When everything is done, the core method of the script starts. On a topic, through MQTT protocol, every 20 seconds, the suggested actuation command for the specific actuator is published. There are 3 different algorithms that decide to turn on or off the actuators. For the lamp, from Trefoil API, the exposure to the sun of the plant is obtained and the real-time value of sun brightness is received on the subscribed MQTT topic. So control strategy checks that the plant receives enough light for the right time during the day. If the sun exposure is not enough, the lamp is turned on, otherwise is not. For the water pump, the control is similar to the previous one. Soil moisture is compared with the reference value got from Trefoil API and the water pump is actuated accordingly. Furthermore, it checks the local time, so that once a day starting from 6 p.m. for 5 minutes plants are watered autonomously. For the fan, in this case what is done is maintaining temperature and relative humidity under maximum threshold values. Moreover, data from environment sensor DHT11 placed outside the box to collect environment data are used and the algorithm activates the fan if it sees there is too much difference between internal and external values of the 2 DHT11 sensors.
Telegram bot provides an easy-to-use interface to interact with the greenhouse. Typing start in the chat, the bot will show the available commands. For instance, I want to read the temperature of the box 1. I'll type read temp and choose the box, and here it is. It's also possible to control actuators. For instance, I'll switch on the light of my plant by typing light on. And there was light. ThinkSpeak is an open-source application to store data and show them in its dashboard. Users will be able to monitor at almost real time the greenhouse conditions. Sensors communicate with ThinkSpeak API using HTTP and MQTT protocol. As we can see, there are different channels showing sensor readings of the box 1. I'm going to cover the light sensor with a reg. the graph goes rapidly to zero. Removing the reg, the graph rises up.
Node-RED offers an easy way to interact with the greenhouse system by exposing a useful dashboard UI that for each box configured shows a tab with real-time measurements from the sensors and the possibility of manually interacting with actuators. As far as the developer part is concerned, the main flow file is composed by multiple flows. First one is the one that defines useful global variables such as a greenhouse catalogs and MQTT brokers IPs and ports, a reference for setting up every communication node. A second group of flows is used for showing box sensors readings. First, an MQTT subscriber node is configured to subscribe to a respective sensor topic. Then a function node through a simple JS code unpacks the payload, that is the sensor reading in SANML format, and assigns to message.payload the reading value. Finally, this value is fed to the appropriate dashboard's widget node to be shown in the UI. The same process is carried out for the environment sensor. The third group of flows deals with actuators. 3 switches are inserted in the dashboard for controlling the lamp, the water pump, and the fan, and the 3 respective nodes are producing a boolean value as message.payload. This message object is then passed to a function node where an appropriate SANML command is composed and assigned to message.payload that is finally fed into an MQTT publisher node that streams the control command on the appropriate topic. The dashboard has a tab for each box in the greenhouse, and widgets are divided in groups such as environment sensors, box 1 sensors, and box 1 actuators. Sensors readings are shown in the UI as a dashboard, and different types of visualization are available. As an example, temperature and oxygen are shown as plots over time, soil moisture as a level meter, and light and relative humidity as gauges. Actuators can be controlled by switches on the dashboard. When the switch is activated for a given actuator, a SANML command is sent over the respective MQTT topic, taking action on the system.